Let's see, where should I begin this discussion about coreboot? Coreboot's open source, meaning that the source code is available for everyone to look at and, most importantly, improve. And it's a perfect companion when I get finally to that point where I start talking about the Linux operating system. In between those two is going to be Grub, the Grand Unified Bootloader. So now it's time to kind of look at the outsides of this thing and figure out why we're in all that guts of the AMD system on a chip, which is the example that I used. AMD seems to be at the forefront. So Intel started all of this stuff with the x86 processor, but I'm going to use AMD as the competitor to Intel and figure out what to do with that. So, what should I focus on when I talk about these different code windows, which you're used to all these code things that I put up there and looking at assembler and C and so on? Let's kind of step back from all that and see, let's put ourselves in the place of a core boot programmer, somebody that wants to improve the source code. When you have source code, you need debugging tools. One very fancy debugging tool is called a JTAG debugger, which actually gets inside the chip and you can monitor bits racing by a certain port and you can see stuff going on all the time. But that's not available all the time. So the next lowest level is using an I/O port, so that in your code you do an I/O port. So we can look at the post code sections of the processor, which is at the real low level before we get some better debugging tools. Then, after we look at post code, we can also look at timestamps. Now, timestamps aren't going to be so easy to track, other than the fact that that'll measure the time that these different sections take. Which to the outsider, he said, well, who cares how much time it takes? That's just the BIOS at the beginning. But have you ever started your system up and seen it scroll and 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 scroll before the operating system starts? What's going on during that time? That's the BIOS running. So the shorter we can make that time, the more efficient our system is. So when we do a restart, it just goes boom, there's our operating system. That's what we really want. So Core Boot is really focused on making things fast. Rather than running everything out of double EEPROM, we run some stuff in RAM and see how fast we can do that. But during the EEPROM stages, we want it as short as possible. So we do these timestamps, and then we can, if we figure out ways to make it shorter, we can look at those two timestamps, calculate what the time is. Now, this is all about Core Boot. Now, what's even better? Well, if we have a console, you look at your screen, you see messages come up that tells you what's going on. But what kind of screen do you normally have on your PC? Well, it's probably a VGA, the graphics adapter to the. It's got, in other words, a VGA. It's a three color VGA thing that sets up and does all the funny stuff. Well, that interface is not available early on. What is available? Well, let's see. How about a UART port? Universal Asynchronous Receive Transmit port. That's old. That's before USB. Before USB. USB replaced UART. So if we go all the way back and talk about the terminal or the console, those were things where you sent 1 byte to the console and it put 1 byte on the screen. ASCII code, ASCII code. which puts up the letters on the screen. And that it didn't have all this fancy graphics and everything else like that. But who has one of those? And where's the UART port on a PC? They don't provide UART ports anyway. Use USB. USB is even a little bit more involved than UART. So who's going to be setting this up? Well, if you're a coreboot programmer, you've got the guts of your computer opened up. And you can find the UART port and use that directly to a low level UART uh, console, or convert stuff, and you can use it with a USB input terminal. But you're buying this hardware just so you can debug BIOS. Well, do we want to debug BIOS? Are we going to change coreboot and make it better? No, we're not. But we can look at the print statements that go to this console and kind of get an idea what the progress of coreboot is. We'll just kind of pretend that we're looking at a console, and I'll dig these messages out so then you can look at them and uh, just see what the different stages are by looking at these debug messages without looking at the code all the time and getting lost in it. So, uh, put on your seatbelts and let's go for a ride through these debug messages. Each one of these represents a constant, which represents an 8-bit code, simple 8-bit code that's sent to port 80. You notice the title of this file is IO port 80. So reset vector correct. Wow, that's real early on. That's real early on. Then what happens next? Enter protected mode. So that happens. Then what happens? Boot block pre-C entry, and then pre-C entry done. What's going on there? Well, that's the cache's RAM assembly junk that happens. Then we go into the C code and we do the system on a chip early init. And fortunately, I'm not going to dive into all the details of the firmware controller hub and all that stuff that I did in an earlier one. Then what do? PSP notified DRAM. DRAM. Okay, that's dynamic RAM. Those are the RAM chips that are on the board. So we're starting to use stuff on the board. Then we finish that up. That says that we're done with that. Then it says run postcar. Run postcar. Oh, okay. That means that we're running the post cache's RAM operation. So in between here, we've kind of completed the Romstage. This has all been a program that's been running out of the RAM in the cache's RAM. So things are speeding up here when we're doing it this way. Then notice entry hardware main. This is really the Ramstage. The Ramstage does a lot of funny stuff here. And let's see. Let me edit this. Looks like I made a mistake. Too many post codes. And let me save that. Okay. And so here we're starting with the hardware main. And then we do, look at all these steps. All of these steps are in this BS, which is a boot state. Oh, not a boot state. It's a, what kind of state? This is the states that we go through in this value to check all the stuff out on the board. So here we're checking out the hardware board. So each hardware main stuff, these have to relate to that hardware board. So we do something called a pre-device. Then we initialize the chips. So that's an important step, initializing the chips. Then we do something called a device enumerate. So we go through and, well, I'd have to look at the code to see exactly what we do with a device enumerate. Then we do resources. Then we enable the devices. Look, we initialized them. Now we're enabling them, and then we're doing the final device oh, this is the device init versus device init chips. Well, we could get down into the bloody details and see what's going on there. Then BS post device. So that's another state that's occurring while we're going through this hardware main. Notice each one of these has a BS on it, so each one of those is a state in this state machine as we go through and do this. Now let's see. We do a post device. That means afterwards. Then we do an OS resume check, and we do an OS resume. We can dig into all these details, but this just gives us a high view. Then we write the tables, and then what do? Wow, we're at the end of the Ramstage here because we're doing the payload load. Now, what the heck is a payload? The payload is what's actually going to load the operating system itself. And that's going to be the payload is going to be the Grub2, which is the Grand Unified Bootloader, where we have open source code, which, hey, more videos. How much fun can that be? Then we do the payload boot. We're starting to get everything set up to actually run the payload. And then we have the final code here, enter elf boot. This is the elf file is the executable, what is that called? Executable, anyway, that's the format, the executable type format, which is a bunch of ASCII codes represents the code, and you can actually load that directly into memory, and then you can start executing it. So here we go, all the way from a reset vector down to loading the payload. So each one of these codes, we could search for it in the code and find out what's going on. So that's a good way to walk through it. All right, kind of got the idea with that? Let's look at another one. The timestamps. The timestamps that occur in the core boot. Let's look at those. Okay? Boot block start and boot block end. We remember those back here on this boot block file. Here was timestamp boot block start and boot block end. Let me go back to that file before I lose my place. Boot block start and end. Copy ROM start, copy ROM end. Where are we copying it? We're copying the ROM file for the Romstage into the cache's RAM memory. So we copy the stuff into there, and then we finally start the Romstage, and finally the Romstage is ended. Then we do the postcar start, which means that we're doing the post cache's RAM start, where we disable the cache's RAM feature and enable the caches back, so it starts running like a regular application processor there, where we load directly from RAM. Now we're copying so that one's all ends up there. Now we're copying the RAM image, the Ramstage image into here. Here's a start and here's an end. And now we're starting the Ramstage. And after the Ramstage, notice the different timestamps we have. Device enumerate, that was one of the states that we were in before. Device configure, device enable, device initialize. All the devices are done. We check out the CB mem, which is core boot memory. Then we write some tables. We load the payload, and then we do a self boot jump. So here's all the timestamps that are in there. So the core boot developer could come up and look at these timestamps and figure out how long this whole thing takes. So from boot block start to self boot jump, that would be how long the screen has to run before the whole thing starts up with the grub. Then we'd see the grub screen, which we'll get a picture of that later. I hope that kind of gives you an idea of what's going on. This is the overview of it. Each one of these we could do separately into the stages. We did boot block. Boot block was low-level initialization of the firmware controller hub. Now it's Romstage. Romstage primarily is to make sure that the RAM is okay before we load program in there. So we can load a larger program, which is the RAM stuff that does all the hardware checkouts and so on, and it's necessarily going to be a larger block of code. So let's look at that code and try not to get too lost. Run Romstage. That was the end of the boot block. And this one's going to be easy until we get into the ROM stage, because all this says is run the ROM stage. So it loads up the file that we're going to run, and it loads it into the cache's RAM area where it's going to run. And then we run the program. Now I've got a surprise for you. Rather than starting out with C code here, we're going back to assembly. And you see this assembly is going to start, typically the start of an assembly program uses the word start. And we go back here and set up some stuff because we're leaving the we're leaving the SPI ROM environment and we're going into this new environment. So we set up the global descriptor table for a 64-bit because we're in 64-bit mode now. And we get the stack pointer and some other stuff like that set up. Let's see what else we got. Anything very interesting. Copy the data to the cache's RAM area. And then this is if you have a JTAG debugger, you can use that for this part. We could do this. We do some other initialization, and then we do a car stage entry. Car stage entry. Hey, look what's there. ROM stage start. Console init, then we go to ROM stage main. ROM stage main. And then the first function we run is SOC enable, and this is a special type of arrangement that the AMD chip uses, and that is called the Platform Security Processor Early. So this is very involved. Platform Security Processor. Well, let's go to the file, and it probably will give us some information that'll help us figure that out. Here we are at the function. It says, let's look at this. This is interesting. Open a posted hole from this address to this address, -1. Well, this side, that kind of makes sense. That's in the area of the SPI ROM that we started at FFFFFFF0, and this is I can imagine this section, but I'm not sure about this 8, because this is at that's a low memory address? It says this is the base. I guess if we posted whole, anyway, obviously I don't know much about that. So anyway, there's some PCI write configs to set that up. We're starting to get off on the side beam here. Let's look at, was it Romstage I was in? See, I didn't even remember which file we came from. Then let's see. Uh, PSP load named blob. PSP load named blob. Let's see if we can find another file that matches up with that. A blob, it says PSP load named blob. That gets off into a big section of code. Anyway, this is probably a topic unto itself. So let's just take that on face value. I filled in what the platform security processor was. It's just that. If you mess up on code, it won't allow you to do something. Okay. Mainboard Romstage entry. That sounds like a major thing. Let's go up here. Mainboard Romstage entry. By default, don't do anything. So we don't need to worry about that. Uh, for this particular processor that I chose, we don't have to do anything there. Then here's something elog boot notify. Let's see if we have an elog file. Elog boot notify doesn't seem to be a very complicated thing, and only this occurs if you have an elog boot count configured. So it says boot count increment. Not going to chase down boot count increment. I don't think that's going to bias anything. Back to Romstage. Where is Romstage? Did we lose it? There's Romstage. Then we have something BSP AGESA call. This stands for AMD Generic Encapsulated Software. Very, uh, very manufacturer specific stuff. So I'm just trying to find some things that really will enlighten us about what's going on. I see some very low level details, and this is really what we want to get to is PSP notified DRAM. This is where the uh, DRAM is initialized. And let's see, does something about coreboot memory recovery. And really, that's not too much more out of this. But you can see that its main thing was to set up the RAM memory so that we can go on to the next stage, or at least get out of cache as RAM. So here's the next step: prepare and run postcar. Here's prepare and run postcar. Fill postcar frame. Postcar frame common. Run postcar phase. Says we do not return here, so we keep moving on. Let's find postcar phase. Run postcar phase. Now, anytime you see this arrangement, prog init, it's getting ready to load something into memory. And the postcar phase is going to be, then it's executed down here. And I'm going to guess that the postcar stage is run in RAM. So let's see what actually occurs there. Here's the postcar stage, late caches RAM teardown. So if we're tearing it down, we must not be in caches RAM when we're running this. Otherwise, we'd have to tear down our own memory. So this must be in regular DRAM, late car teardown. in this case, we don't have to do anything. I love it when we don't have to do anything. And then we run the Ramstage, which will be in the main board operation. So we're ready to do the Ramstage. Remember, the Ramstage is right before we load payload, so we're almost getting there. Ramstage. Let's get going on this. Ramstage. Here's a Ramstage Ada init, which allows you to use the Ada code. Not really that interesting. We've got the console init. Here's that postcode, console ready. Exception init, that allows the interrupt exception to be properly handled. And we do the wake up, and then we do this thing called BS walk state machine. Let's find out where the state machine is. Notice that that's the last thing we do in the Ramstage. BS walk state machine. While one. That means we're in we'll never get out of this loop. While one, we'll never get out of there. Well, there's got to be some way to get out of it. Somewhere in this code, we exit here. But what happens is we go through each of the hardware test states for the main board in Ramstage. And of those different phases, we're going to go through all those things that we saw on the uh, was it timestamp or was it uh, postcode? I think we had a combination of it on both of them, but each one goes through all the different steps to initialize the chips, get everything done. I might do if it's that interesting, I might do another software, another 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 video just on initializing the chips. I know I want to get into that more uh, detailed so that I can figure out how all this, that's part of understanding how all this stuff works. But anyway, when we finally get done here, it passes it from one state to the other until finally the whole thing ends. Here's how we get out of the while loop. It says boot state payload boot, which means that eventually we run the payload. So when we run the payload, that means that we're running their grand unified bootloader. So I hope that kind of ties up the knots on that. Here endeth coreboot. There's a lot of details in coreboot that I haven't covered, but I think that's enough for this overview video. I'm looking forward to the grand unified bootloader because then we can start thinking about loading the Linux kernel in and really getting down to the tacks of how an operating system works. That's really what I want to do. That's really what I've wanted to do for a long time is learn about the operating systems. So guess what? I can learn about the systems that use the quantum computing platform, which is where I'm really headed. So if you want more details in coreboot, you want me to dig deeper into that from this overview, then please leave comments and I'll be glad to go into those details.